Hey everyone, welcome to Neural Notes, show where AI comes alive. Smash that subscribe button and ride the innovation wave.
Hey there, and welcome. Today we're diving into a topic that can sometimes feel a bit, well, mysterious: calculating limits. But what if I told you it's really just a puzzle? And, like any good puzzle, it all starts with one surprisingly simple first move. So, let's get into it and break it all down. Here's the game plan for today. We're going to start with the single most important shortcut you'll ever learn for limits. Then we'll build up our toolkit with some really useful laws. After that, we'll explore the two big scenarios you're going to run into: the nice, easy answers and the tricky ones, before we tie it all together into one simple, powerful strategy.
All right, let's kick things off with Section 1, the limit calculation shortcut. And I mean it when I say this is the one rule you need to start every single problem.
So let me ask you this. You're looking at a limit problem. Maybe it looks a little intimidating. What is the absolute first thing you should do every single time? No exceptions.
And here it is. This is the big secret, your absolute golden rule. Just plug the number in. Seriously, before you try any fancy algebra, before you do anything else, just take the number that x is approaching and stick it right into the function. It's the simplest but most powerful first step you can take.
But, this isn't just some random trick. There's a solid mathematical reason behind it, and it's called the direct substitution property. All this really says is that for most of the well-behaved functions we deal with, polynomials, rational functions, that kind of thing, if the point you're heading towards is actually in the domain, well, the limit is simply the value of the function at that exact point.
Okay, so on to Section 2, your limit law toolkit. Because, let's be real, sometimes the expressions look a little more messy. So what do we do then?
Well, that's where these limit laws come in handy. The big idea here is that they let you break down a big, complicated expression into smaller, bite-sized pieces that are way easier to handle. So the limit of two things added together? It's just the limit of the first plus the limit of the second. Same goes for subtraction, multiplication, you get the idea. It's like taking apart a complex engine to see how each individual part works.
And check out this example. It's a perfect way to see this in action. We need to find the limit of this whole combination of functions. And get this, we don't even know what the functions f of x and g of x actually are, but it doesn't matter. Using those limit laws, we can just split the problem apart, plug in the limit values we do know, and do the simple math. So we get 5 times 3 minus 2 times negative 2, which gives us a final answer of 19. Pretty cool, right?
All right, Section 3. Now this is the one we're always hoping for. This is Case 1, the simple answers. This is where that golden rule of ours just pays off instantly.
It's exactly what it sounds like. If you plug in that number and you get a real, honest-to-goodness number back, could be 5, could be negative 1/2, it could even be 0, you're done. That's it. That number is your answer. Game over.
Let's walk through this one together. First step, always the same: direct substitution. We plug negative 3 in for x. On top, we get the square root of 1 minus negative 3. That's the square root of 4, which is 2. On the bottom, negative 3 squared is 9, and minus 4 times negative 3 is plus 12. So 9 plus 12 is 21. And there we have it, a clean, simple answer: 2 over 21. Problem solved.
And here's one more, just to really drive it home. We want the limit as x approaches 0. So what do? We plug in 0. The numerator becomes 0 minus 0, which is just 0. The denominator becomes 3 plus 0, which is 3. So we have 0 divided by 3, and that's just 0. That's a perfectly valid number, so that's our limit. See? Simple.
Okay, so far this seems, well, pretty straightforward, right? But what happens when our simple substitution method seems to break? Well, welcome to Section 4 and what I like to call the infinity clue. So you do everything right. You follow the golden rule, you plug in the number, but the result isn't a nice, clean number. The result you get is, well, it's something a little strange.
Yep, this. A non-zero number sitting on top and a big old 0 on the bottom. We're trying to divide by 0.
Now, your first reaction might be to think, oh no, it's undefined, I messed up, right? Is the math just broken? What on earth does this result actually mean? It's not an error. In fact, it's the exact opposite. It's a huge clue. Getting a non-zero number over 0 is the function screaming at you that you've just found a vertical asymptote. It means the function isn't settling down to a single value, it's rocketing off to either positive
or negative infinity.
Okay, let's really pick this one apart. We plug in 1, and we get -4/0. Ding, 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 that's our clue. We know the answer is either positive or negative infinity. Now we just need to figure out which one. So we test a number that's super close to 1 but on the right side, something like 1.1. The numerator, -4, that's obviously negative. The denominator becomes 1 minus 1.1, which is -0.1. So think about what's happening. We have a negative number divided by a tiny, tiny negative number. And what happens when you divide a negative by a negative? You get a positive. So the limit has to be positive infinity.
And that brings us to our final section, where we pull all these threads together. This is your limit-solving strategy, a complete plan of attack for any problem that comes your way.
So let's recap the two main paths we've seen so far. Case 1, you plug in the number, you get a real answer, and you're done. Case 2, you get a non-zero number over 0, and you know the limit is infinite. But hang on, there's a third critical outcome we have to talk about. What if you get 0/0? Now this isn't a final answer, and it's not infinity. It's something called an indeterminate form. And it's basically a clue that you need to do a little more detective work, usually some algebra, like factoring, to find the true limit hiding underneath. It's the most complex case, but honestly, it's often the most interesting one to solve.
So when you boil it all down, your strategy is really a simple decision tree. Step 1, always, always, always plug in the number first, no matter what. Step 2, look at your result. If it's a clear number, you're done. That's your answer. Step 3, if it's non-zero over 0, you know it's going to infinity, you just have to test the signs. And if it's that special 0/0 case, well, that's your signal to roll up your sleeves and do some algebra. Your first step literally tells you exactly which path to take next.
So, we've spent all this time learning the how, the practical steps to find a limit's destination. But that leaves us with a bigger question to chew on. Whether that destination is a simple number, like 2/21, an explosive blast towards infinity, or a hidden value you had to uncover from 0/0, what does that final destination truly tell you about the story of the function? What does it reveal about its journey as it gets infinitely close to that one special point? Now that is something we're thinking about.